Hi, today we are going to talk about efficient segmentation models, which we crafted for resource-constrained environments. My name is Bilge Soran. I'm a research scientist manager in Meta Reality Labs. I created this presentation with Yunyang Xiong, who is a research scientist also from Meta Reality Labs. Image segmentation is the process of dividing an image into its individual elements or objects and identifying boundaries between them. The segment anything model is a type of AI model developed by Meta AI that can be used for image segmentation tasks. It has the ability to segment anything in an image, including objects and scenes, while being promptable. SAM did create a big stepping stone on the image segmentation domain. There were lots of attention from the research community, but it had some performance gaps for on-device usages. First of all, SAM is too large to deploy on a resource-constrained device and requires GPU to get a single answer from the model within a half second. This creates scalability concerns, as the computational capacity need increases with the amount of usage, as well as the latency issues arising from half-second inference wait time per single frame. We needed a small, fast, and high-quality segmentation model with low inference costs. To address these limitations of SAM, we proposed EfficientSAM and SqueezeSAM, which are state-of-the-art models without the latency, model size, and capacity problems. Today, we will cover EfficientSAM and SqueezeSAM and our current investments in segmentation efficiency as part of our future work. We will start with describing EfficientSAM. Yunyang is going to talk about it next.
Now I'm going to cover EfficientSAM. SAM model is decent and it shows impressive instance segmentation performance, but we know it's too large to deploy on client and require high-end GPU like A100 and H100 to get a simple answer from the model within a half second, due to the heavy image encoder, which has 600 million parameters. So we needed a small, fast, and high-quality segmentation model specifically crafted for on-device deployment. Therefore, we created efficient versions of it. EfficientSAM is a smaller and fast version of SAM, and more importantly, it achieves an impressive segmentation quality compared to SAM. For this work, our goal is to reduce the complexity of SAM while maintaining the impressive quality. This figure shows what EfficientSAM achieved. On segment anything tasks such as zero-shot instance segmentation, our EfficientSAM with semi-pre-trained lightweight image encoder is within 2 points of the original SAM model, like 44.4 AP versus 46.5 AP, but with 20 times fewer parameters and 20 times faster runtime. It also outperforms other fast SAM models by a large margin, 4 AP on Coco Elvis instance segmentation benchmark, with comparable complexity. This largely reduced complexity while maintaining decent quality enables EfficientSAM for on-device applications. Our idea is based on leveraging masked image pre-training SAMI, which learns to reconstruct features from teacher SAM image encoder for effective visual representation learning. And further, we take semi-pre-trained lightweight image encoders and mask decoder to build EfficientSAM and fine-tune the models on SA1B dataset for segment anything task. For SAM leveraged masked image pre-training, we are taking SAM as a teacher and use the teacher to distill knowledge for the student, a mask autoencoder. And for the student mask autoencoder, we follow the traditional architecture, transformer encoder and transformer decoder. And since our goal is to have a quality lightweight encoder, we use mask autoencoder with lightweight encoder as masked encoder, and cross-attention decoder as decoder for helping transfer SAM's teacher for image segmentation. For EfficientSAM, we adapt the architecture, transformer encoder, and mask decoder of original SAM, and we use a pre-trained lightweight vision transformer VIT from SAMI as the image encoder, and the mask decoder from SAM for helping build EfficientSAM. To perform segmentation anything task, we fine-tune in EfficientSAM on SA1B dataset for quality improvement. We now provide some experimental results to demonstrate the distant instance segmentation performance. On the zero-shot instance segmentation, with taking the bounding box generated from VIT.dat as a prompt, EfficientSAM more significantly reduced the gap between SAM and with 600 million parameters, only like 2 AP reduction. We also compare our EfficientSAM with mobile SAM and fast SAM. We can see that EfficientSAM Small obtains more than 6.5 AP on COCO dataset and 7.8 AP on Elvis over FastSAM. Note that our EfficientSAM are much lightweight than FastSAM. For example, EfficientSAM Tiny only has 9.8 million parameters, but for FastSAM, it has 68 million parameters. It's almost 7 times larger. And these results demonstrate the extraordinary benefits of EfficientSAM for efficient instance segmentation. We further provide the qualitative results for a complementary understanding of instance segmentation capability of EfficientSAM. We show that our EfficientSAMs having computing capability when comparing to SAM with different prompts, point prompt, box prompt, and segment everything. So in the figure, we show the original image and EfficientSAM outputs and original SAM outputs, and they are very similar for visualization. We also extend EfficientSAM to salient instance segmentation without manually creating box and point prompts. And this preliminary explanation opens the potential to help people with hand impairments segment objects of interest in an image. Until here, we have covered EfficientSAM, and Bilge is going to talk about SquidSAM, another efficient segmentation model for interesting practical needs.
I want to start this section by mentioning the need for auto-creation. Segmentation models, if not trained specifically to segment out particular object categories, require user input to cut out the object of interest. However, we needed a solution that is fast and doesn't require user input to cut out the desired object. Therefore, we needed to estimate the object of interest. We achieved this by utilizing a saliency model and simulating user clicks. Saliency model outputs a heat map representing the prominency of different image regions. We processed the saliency map and created simulated user clicks using a novel approach we call as gravitational sampling, as shown in the bottom image. Then, those clicks are sent to the segmentation model to cut out the prominent objects in the image. Let's look at the pros and cons of using the saliency model for simulating the user input. First of all, saliency models we use are fast and compact and also suitable for on-device usage. The saliency map can cover multiple prominent objects together, which suits to our purpose. We are neither interested in instance segmentation nor semantic segmentation. Our solution lays in between, as shown in the bottom right picture. We are interested in whole object segmentation. But saliency maps are not perfect. The auto-created clicks sometimes may not fully align with the user intentions. One can overcome this by prompting the model with actual user input. SquidSAM consists of an encoder-decoder architecture, where the encoder embeds the input image into a rich intermediate representation, and the decoder consumes this representation along with user clicks to produce a set of segmentation masks. The proposed idea of early fusion combines the input image with the user clicks to be sent to the encoder, allowing the model to pay more attention on the image regions that the user wants to segment. In addition to this early fusion, points are also encoded using the decoder transformer as is done with the original SAM. The mix of early and late fusion helps the model further in being able to attend to the sought objects. As shown in the far right group of figures, SA1B dataset has many annotations for object parts. We found this type of annotation hurts our model's performance on the whole object segmentation problem. For this reason, we pruned the SA1B dataset by applying a list of data augmentation techniques, such as suppressing small masks within a larger mask, or removing objects with tiny regions, and merging masks within a ground-truth bounding box. We have developed a fully convolutional EfficientSAM model architecture, which is about 63 times faster and 32 times smaller than the original SAM, making it a viable solution for mobile applications. We performed both quantitative and qualitative evaluations. Quantitative evaluations are done on the ELVIS dataset using the MIOU metric. When the saliency estimation added to our evaluations, our model beats the original SAM model with a large margin, while being 63 times faster. In our qualitative evaluations, we used a scale of 1 to 5, 1 being unacceptable and 5 being the perfect segmentation output. EfficientSAM achieved 4.2 scoring on this evaluation, while performing even better for the people and pets categories. As you can see from these qualitative results, EfficientSAM does a much better job than its counterparts on whole object segmentation, which also improves instance segmentation for some object categories composed of multiple parts, such as the flower on the bottom of the figure. While the original SAM could only segment out only a leaf of the flower, with the same prompt, EfficientSAM able to cut out the whole flower together with its stem. Until now, we have covered EfficientSAM and EfficientSAM models for efficient image segmentation. You may wonder how these models can be extended for efficient video segmentation. I will start with a brief recap of SAM2, the video segmentation model from Meta AI. Similar to SAM, SAM2 is a foundational model designed to tackle visual segmentation tasks in both images and videos. Building on the original SAM, it now handles video by treating still images as single-frame videos. The model features a straightforward transformer design with streaming memory, enabling real-time processing of video content. Next, Yunyang is going to cover our recent work on efficient segment anything on videos.
For this work, our goal is to extend EfficientSAM for efficient video segmentation while maintaining impressive video segmentation quality compared to our baseline SAM2. And this figure shows what EfficientSAM video achieved. On video segmentation anything task, our EfficientSAM video is comparable to the original SAM2 model with more than twice faster runtime. Our EfficientSAM video also enables on-device video segmentation on iPhone 15, like 200 milliseconds per frame with decent video segmentation quality, which is complementary to SAM2 for on-device deployment. We now provide some experimental results. This table shows our EfficientSAM video achieves reasonable performance on video instance segmentation benchmark comparing to SAM2. Our EfficientSAM video achieves 74.5% accuracy on test dataset. SAM2 has 74.7% accuracy as a baseline. From the number we can see, these models are performed very comparably, and EfficientSAM video is much efficient than SAM2. So from these results, we can see our EfficientSAM video is quite comparable to SAM2. Note that our EfficientSAM video is much efficient than SAM2. Until here, we have covered efficient instance segmentation for images and videos. We have some takeaway message for you. EfficientSAM, EfficientSAM are very friendly for efficient instance segmentation on server, local, and device. And EfficientSAM video can serve as unified image and video segmentation for server, local, and device deployment. The last point is our model also supports out-instance segmentation without manual clicks. This helps reduce the manual efforts for picking clicks and objects. We also provide some future directions. We are interested in building on-device EfficientSAM video demo for unified image and video segmentation. This helps our users to play with Meta's state-of-the-art techniques. We also want to support a zero-shot open-set segmentation by leveraging large language models, Llama, for understanding users' interests. Like one example here is, when user want to segment the dog in the image, and user just need to talk to their phones or type running dog, and then our demo will provide you the segment object of the dog. And we are also exploring more use cases of EfficientSAM for AR, VR, and smart glass applications. We all know Meta has provided many hardwares, and the smart glass, label smart glass, is very popular for recording videos and taking images. And these techniques from Meta can also open the potential to combine this advantage of EfficientSAM for smart glass videos and images segmentation. And that's all for today's talk. Thank you.